moving restlessly and eternally over the face of the earth, is one of the most effective agents of gradation. It is the atmosphere. Powerful in its own erosive right, the air is even more important in forming and transporting great clouds, which precipitate their water vapor in the form of rain or snow. The atmosphere thus becomes an ally of water and ice, two other major agents of gradation. Wall crevices may freeze, thus aiding in mechanical disintegration of rocks. Freezing also facilitates gradation by prying up and loosening soil. On the other hand, in arid regions, rock surfaces crack under the stresses of alternate expansion due to baking by day and cooling by night. The chemical action of moisture in the atmosphere enlarges these cracks and thus aids temperature changes to disintegrate the rock. In some localities, this atmospheric activity results in the peeling of rounded scales of solid rock. This process is called exfoliation. It may help to round rock masses as large as Half Dome in Yosemite. The sharp, fresh edges of many rocks and jagged peaks in cold regions and high altitudes are evidence that they have been broken by mechanical rather than by chemical activity. A striking result of such disintegration is seen in the huge talus slopes or tumbled masses of broken rock at the bases of some cliffs. But it is the chemical activity of the atmosphere, aided by moist, warm climate, that has disintegrated this rock. Note the resulting rock debris at the side. Even more spectacular are the results of the erosive action of wind, the Earth's atmosphere in motion. In dry regions, the wind carries along with it great quantities of sand, each grain an effective erosional tool. A highly magnified view of several sand grains shows their sharp cutting edges. Such hard quartz grains cut into solid rock when blown across its surface. Thus, the wind is always acquiring new tools in the form of debris which it cuts out of every rock it erodes. This sandblast abrades all exposed surfaces, and here inequalities in the rock's resistance to the atmosphere's agents have resulted in these rounded and honeycombed formations. This same sandblast action uncovers and scours the roots and the trunks of exposed trees. Note the sandblast effect on the bark. In arid regions, the lower portions of telegraph poles may be gnawed by the cutting teeth of wind-blown sand unless they are given protection. In some places, the wind sweeps the sand along and deposits it in great heaps called dunes. On the windward side, the dune rises gradually. But to the lee of its crest, the sand swirls and falls to form a steep slope. Changes in the direction of the wind result in the sands being cross-bedded. The story of the formation of a large dune is repeated thousands of times in the growth of miniature dunes or ripples common to its windward side. Dunes march forward in the direction taken by prevailing winds and may bury buildings or even forests. Since heavy vegetation on the windward side may check or stop the advance of dunes, there is a constant struggle between shifting sands and growing grasses, shrubs, and trees. Ages ago, the winds piled up the restless sand into dunes just as they do today. In many places, ancient sediments reveal cross-bedded dune structures and ripples whose sands long since cemented to form hard rock. Banks of less, hundreds of feet thick, occur in many places, notably along the Mississippi River. They were formed by the winds lifting fine dust-like particles of rock to great heights, carrying them for great distances, and then depositing them in such banks. Throughout dry regions and where soil has been laid bare, particularly through cultivation, wind sometimes gathers up the dusty soil and carries it along in thick, blinding clouds. Rising to great heights, this dust may gradually settle over a vast region hundreds of miles across. Here is the portion of North America affected by a single dust storm. Great dust storms also originate in the Sahara and move northward. One of these deposited a thick blanket of red dust over much of Central Europe. In a similar way, uprushing air currents carry vast quantities of dust from erupting volcanoes and transport the material great distances. Such dust from an explosion of Mount Katmai rose to a height of 15 miles and was carried completely around the Earth. The transporting of fine sand, dust, and ash is the most obvious direct work of the atmosphere. But the atmosphere is also essential to the gradational work of water. Clouds of water vapor carried high into the atmosphere may come in contact with cooler air. This lessens the cloud's ability to hold water. The moisture, gathering about minute floating dust particles, condenses to form small drops of water. These become so heavy that they fall to the earth as rain. The atmosphere also works hand in hand with surface water. The light edges of this common rock, largely composed of feldspar mineral, have been chemically altered to form clay. Under the microscope, the feldspar appears coarse and crystalline, in contrast to the fine, powdery texture of the clay. Near the surface of the ground, carbon dioxide and moisture from the air decompose certain rocks to form clays and sands. Rainwater, descending from the surface, transports the fine clay downward through the coarser soil. In this way, beds of clay have been building up since the Earth first developed an atmosphere. In ordinary soils, therefore, sandy material predominates near the surface, whereas clays accumulate in the lower subsoil. By its depositional and chemical action, the atmosphere thus helps to create the soil. Fertile soils sustain plant growth, without which animals could not exist. And both plants and animals depend on the air for their very life breath. We have seen that this gaseous, earth-enfolding blanket, the atmosphere, quietly causes important chemical changes. Its great erosive work is apparent as it cuts with sharp-edged particles of sand. We sense its transportational importance when the air is choked with dust. We see its relation to the work of water as we watch rain fall. And we all benefit from its significant role in the formation of soil. Without the atmosphere, all things would disappear from the surface of our Earth. Like the moon, it would wheel eternally along its orbit, baked by day and frozen by night, a barren, lifeless, uneroded sphere.